Okay, there we go. All right. So the first part of the chapter, one of the first drawings you did, had a chart, and it talked about, you can just put those back there. It has solids, liquids, and gases. Is that right? These are called states of matter. Usually when you get older, certainly when you get to college, they call them phases of matter. It's really the same thing. There are some people, some high-level physics people, that think there are many states of matter. Right now, I'd say the ones that you're going to run across are solid, liquid, gas, and plasma. Have you heard of plasma? So it's kind of a fourth state of matter. I just read an article that they think water has maybe 8 states of matter. And that's some people that get into high-level physics, and they do stuff. They put it under extreme pressure, they use lasers to try to... Anyway, I've heard of that. We don't study that in high school. That would be something if you become a quantum physicist, you might study that. All right. We already talked about what matter is. And what we're going to talk about now is this right here. If you were a solid and you were going to change to a liquid, why does that even happen? What is the theory behind why that happens? And the fancy way of saying it is called the kinetic theory of matter. Now, you know what kinetic energy is? Everybody? Did you have that? Did you have that in middle school? The energy of motion? Okay. So here's the theory. If you're not at absolute zero, then your particles have some kind of motion to them. See my hands moving? See that? Now, what if I were to take something like ice? What if I had ice at like minus 100 degrees Celsius? You say, well, wait, ice forms at 0 degrees Celsius. Yeah, but what if you make it colder? What if I take ice to some place where it's minus 100? Then the ice becomes minus 100. The kinetic theory says that if you have something that's warmer next to something that's colder, what's going to happen? The particles are moving faster here and they're moving slower here. When I collide with you, I'll give you some of my kinetic energy. You will warm up. You'll take away some of my kinetic energy and I'll cool off. You know what happens? when you touch something, and it's cold, what else happens?
Your fingers get cold.
You know why you say cold? Because you're really terrible at telling temperature with your fingers. You know that? You're terrible at it. Like, if you want to go home and do something, really need a little experiment, get some kind of warm water and some cold water, ice water, okay? And then have a bowl of room temperature water. All right? If you want to try this, you'll be amazed. You'll say, oh, I can't believe that. And you say, I'm good at telling temperature. No, you're not. I'll show you why. So you put your finger in the cold water, you put your finger in the hot water for about 30 seconds, and then ready? Then you put the hot finger into the room temperature water. And you know what it's going to feel like? No. Cold. And then you put your cold finger in there, it goes to feel like hot. And so each finger will say, it's hot, it's cold, it's hot, it's cold. And you say, wait, what happened to me? Here's what you're really good at. You're really good at telling whether or not heat left your body or heat entered your body. That's what you're good at. And so, does this make sense what I'm talking about? All right. You're not going to like this either. Let's say you got up in the middle of the night and you're walking on some carpeting. Maybe you had some carpeting in your room. And it was dark and you were kind of stepping around. And then you stepped on something that was cold. And you found out later, oh, that was a nickel. I don't know how a nickel got on my carpeting. It was there. Is that possible? Is that possible that the nickel was colder than the room? No. If the nickel was colder than the room, then what would the particles of air do when it hits the nickel? If I have this much kinetic energy and you don't, when I hit the nickel all night, then the nickel is getting more kinetic energy and more, and so the nickel is warming up and the air will cool down, and eventually everybody will be the same temperature. So why is it that you swear that the nickel is colder, don't you? Because nickel is a good conductor of heat. It conducts heat away from your foot. It wasn't colder. If you put a thermometer on the carpeting and the nickel, same temperature. But which one can take heat away from your body? The nickel. And that's why your brain says cold, because something took away heat. Are you with me a little bit? Think a little bit different. Now, so let's go this. Let's say you had some really cold ice and you put it in a beaker and you start heating it. The cold ice would start moving a little more and a little more. And the thermometer says you're moving faster, and that's why the thermometer goes up. The thermometer tells you when it goes up, when the particles are moving faster. So what do you call it when you go from solid to liquid? There will be a temperature, and it's called the melting point. The melting point for water, for H2O, what is the melting point for water? It's the temperature, 0 degrees Celsius, isn't it? It's the temperature at which it changes from a solid to a liquid. Now, you had that in middle school and probably elementary. So that shouldn't be a big problem for you. What would happen if you continue to heat the water? The theory is that the particles of the water will bounce further. And by the way, I forgot to tell you this. The reason they were in a solid form is they were attracting each other, and then they start moving faster, and they kind of run into a neighbor, and they push your neighbor a little bit further away, and a little bit more, and eventually it changes into a liquid because there's enough space that it can flow like a liquid. What happens if I keep heating the liquid? And now the particles are moving faster, and they're hitting their neighbor, and they're bumping it, and they're making a little more space between the particles, and then when we get to enough space, it changes into a gas. And what do you call that? Everybody. Sean, if you're paying attention, what do you call it?
What did you say?
When you go from a liquid to a gas. All right. Boiling is what it's called, but what is the boiling point? Boiling point is the
temperature.
It's the temperature at which this occurs. What is the temperature at which it occurs? Isn't the boiling point of water 100 degrees Celsius? All right, boiling is what's happening when it changes from a liquid to a gas, but the temperature at which that occurs is called the boiling point. See the difference? Now, I'm not going to get into plasma today, but if you were to heat it, you could heat particles and they'd be bouncing so much, they'd be going so fast with so much kinetic energy that the atom itself would kind of come apart. And you'd have electrons that used to be around the nucleus, and now they're not. And so you'd have the nucleus, which is positively charged gas, and then the electrons are negatively charged, and this stuff would be called plasma. Now, usually plasma is a very high temperature, and you can't just put it in a bottle because it'll rip up the bottle, it'll tear up the bottle. So you know what they do? It's a little high level. It's okay, a little high level stuff today. The plasma is a bunch of positive nuclei and negative electrons, and they're just bouncing around like this. And so what you do is you use a magnetic field. A magnetic field, because they're charged particles, you could trap them. You could trap them in a magnetic field, and they wouldn't actually touch the actual size of a bottle. It'd be a magnetic bottle. Anyway, they do experiments like that where they trap plasma, and then they might shoot a laser in it, try to excite it even further, and stuff like that. Again, I'm not going to talk too much about plasma today. Now, another word for boiling is vaporizing. Do you remember the candle? The candle went from a solid to a liquid, and when it got near close to the top of the wick, what happened to it? What happens to wax? It vaporized, didn't it? And that's really what burns. Vaporized candle is what burns. Now, let's go the other way. If this is adding heat, which eventually adds kinetic energy, what if we were to take kinetic energy away? What if we were to cool a gas? What would you call it when a gas changes back into a liquid? Matter of fact, that demonstration I showed you the other day where you had the salt water, I changed the water boiled into a gas, and then it went to the other tube that was cool, and what happened? It changed from a gas into a liquid. What do you call that? What's that word? It means you're changing back from a gas back into a liquid. Okay, so that's condensation. Everybody got that? It condensed, didn't it? Now, what if you were to let the liquid cool more and more And more, what would you call it if it went from a liquid to a solid? All right, solidifying. And we like to use, if we're water especially, what do we like to use? Freezing. Or what if I took liquid gold and let it turn into a solid? It'd be solidifying, wouldn't it? And I want to tell you about one neat little one. There's almost all forms of matter go through these stages, these phases, all right? And the theory is everything can do it. But we have a few items on the earth, and God's being kind of, maybe like, I'll just give you something different here. We have some objects that go from a solid and directly into a gas, and you never see the liquid. That's weird. Does anybody know one of these two materials? There are two materials you would have heard of. Does anybody know one of the materials that actually goes from a solid directly into a gas? You never see the liquid. Anybody? No teacher ever taught you that or anything like that? Okay, so the one I know of that you probably heard of is dry ice. All right, so if I had a piece of regular ice right here and a piece of dry ice, the regular ice would probably be at about 0 degrees Celsius. 0 degrees Celsius. And that would be the regular ice. The other one would be about negative 110 degrees. That's Fahrenheit. This is 32, sorry. So I could have some ice, some regular ice at about 32 degrees Fahrenheit, and I could have some dry ice at minus 110. And if I laid them both on this table, there's enough heat in this room that it would heat both of them up. Now, one of them very quickly would start having a liquid underneath it, and that would be the regular ice cube. It would be melting, wouldn't it? But what happens to dry ice? You'll never see a pool of any kind of liquid there. First of all, it's not even made of water. What is dry ice made of?
Nitrogen.
Somebody had to have told you sometime.
Nitrogen.
No, there is liquid nitrogen. You can buy liquid nitrogen, which is even colder than this. No. I can actually buy it at Harris Teeter. You know that? You can buy oops, I gave it away. You can buy dry ice. What's it made of? Oh, I didn't say the whole word. So dry ice is what? Frozen carbon dioxide. So if you take that, you'll never see a puddle. If you were to take a piece of dry ice and put it in a Ziploc bag and sit it there and wait a little while, the bag would get brr, 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 boop, and it would pop. Where's all the extra gas coming from? It's the dry ice changed it to a gas and took up more space. Anyways, fancy name is sublimation. It's sublimes. Get that? It's sublimation. The only other thing I think you've ever heard of in your life is not everybody uses these anymore. I don't think hardly any of your parents, maybe you do. Anybody have parents or grandparents that still use mothballs? Do you know what mothballs are? Do you know why they made them? Have you ever smelled them? Okay, so what happened is there's these little insects called moths, and if they get into your closets, there's certain kinds of fibers they'll chew on, and they'll actually make holes in them, especially wool. And so people a long time ago, there was one way to keep the moths out, and one way is this wood called cedar. Ever heard of cedar? It has a great smell. You know what cedar is? So they have a chest, and it would be a cedar chest. And you can put your wool sweaters in there, and insects hate that smell. They hate it, so they stayed out. Now, not everybody could afford that. The more rich people, they had a whole closet that was lined with cedar. They put all their clothes in there. But most people, say, that costs a little bit of money to do that. And you could go buy this stuff called mothballs. And a mothball, it looks like a little piece of ice. It's not cold at all. It's a little round ball. And immediately you'll start smelling the gas. And if you watch over time, that little ball gets a little smaller, and you never see the liquid. And that's the other material I think you would have maybe heard of, that's sublimation. All right. So are you okay on this side here? Again, it's not knowing the words in this chapter, it's comparing and contrasting the words. All right. Let's go to the other page. Now, this right here, I probably will have something like this on the test. I'll probably have a chart like this. But You need to understand the chart. You can't just say, I'm going to memorize the chart. That's like being a weak student. You're a very weak student if that's what you're doing. All right. Ready? Now, here's something they did in elementary school, and I'll tell you what I think they did in elementary school or middle school. They would say things, what are the properties of a solid? They'll say, does a solid have a definite shape? And let's take a look. Here's a solid. Watch now, watch. Did it keep its shape? It did. It has a definite shape. How about volume? How much space you take up? What do you think? Is it taking up the same amount of space? That was easy, wasn't it? You know, the middle school teacher never did ask you, though. Why? Why does it have a definite shape and definite volume? They just wanted you to memorize that chart, didn't they? But I'm going to ask you a different question. Why? I have another question they're probably never asked in middle school. Can you compress this stuff? Can I take a solid and can I compress it and make it take up less space? And I will tell you that you could take a piece of steel and you could squeeze it and it'll be not as tall, but guess what it will be then? It'll be wider. But guess what? That's the same volume. You cannot take a solid and squeeze it into half of its volume. Why not? One more time. Why? Why? And why? Tell me why. And that's what they don't do in middle school. They just want you to memorize the chart. All right, what do you think? Okay. Demonstrate. Okay. All right, here we go. Ready? Who wants to take a chance? Yes, all right, Ben.
What's the question?
Okay. Why does a solid have a definite shape? Why does it have a definite volume? And why can you not compress it?
Because they're like so closely compact.
You're right. You're right. They are so close. There's essentially no space between the particles. That would explain that. They are so close that they each attract the next door neighbor so much that even if I do this, it keeps its shape, doesn't it? That's why we think solids have those properties. Now, let's go to the opposite end. Let's go to gases. Do gases have a definite shape? If I took a balloon and it has a shape in the balloon, what if I squeeze the balloon? Does it have a different shape? So do gases always have the same shape? No. Do they have the same volume? Do you know I can take all the air in this room and use a compressor and put it in a scuba tank? I can take all this air and put it in a scuba tank. Do gases have a definite volume? Do they have this volume or can they have this volume? They can have many volumes, can't they? And are they compressible? All right, let's have somebody else. How about Hayden, you want to try it? Why do we think gases don't have a definite shape? They don't have a definite volume. And why is it we think, yeah, you can compress them?
Because
Say it again.
they're atoms are all they're not close to each other at all. They're all spread out.
Yes.
So
They're so spread out, they don't attract each other at all. They don't attract each other at all. This particle over here, this little nitrogen over here, it's not attracting this guy over here at all. So it can't keep it in the same shape. It can't keep it in the same volume. And there's so much space between them, you can compress them. I'm just looking at your faces. Your face is the only way I can tell what's going on, okay? Right, Sean? Okay. All right. So now, here's a problem. Let's go to liquids. Liquids, do they have a definite shape? No. If I have a really tall glass of water and I put it into a bowl, it used to have this shape. All of a sudden, it has this shape. So it doesn't have a definite shape. What about definite volume, though? If I had a quart of water and I poured it into a bowl or a baking dish, would it still be a quart of water? Yes. So now we got a problem here. This says that you're acting kind of like a gas. What is this saying? you're acting kind of like a solid. So here's the problem. Here is the problem. I know what you're going to tell me because I know I think they still teach this in middle school and even elementary. I think they teach it wrong. I think a lot of the books even teach it wrong. It's called I call it the Goldilocks problem. Remember Goldilocks? Went to the bear's cabin.
Bears.
And remember Papa Bear's bowl, it was really, really big. I'm going to tell you a little physics here, okay? You're going to be sad. It's going to be a very sad story. But Papa Bear's bowl was full of porridge. You know what? It had so much heat in it and only a certain amount of surface area. No wonder it was too hot. It didn't have enough surface area to cool it off. And then Papa Bear's bowl, it was too hot, wasn't it? Then one of the Mama Bear's bowl is always shown as smaller than that, isn't it? And what did they say about Mama Bear's bowl? It was too cold. You know why it's too cold? It must have had so much surface area per porridge that it got rid of all of its heat. No wonder it was too cold. But here's a sad story. They always show Baby Bear's bowl, and they say what? Too hot, too cold. What was Baby Bear's? Just right. Can't be. That can't be. If Mama Bear's bowl was too cold, there's no way a smaller bowl is not going to be too cold also. So the reason I bring this up, this Goldilocks story, is because here's what every one of your brains doing right now. And they do it in middle school, they do it in elementary. Liquids, solids are really, really close. Gases are really, really far apart. So where are liquids? I know you want to say it. In between. Just right. Isn't that right? I'm going to tell you that's false. If you have been taught that, you got to get rid of it. How do you know it's false, Mr. Finney? I saw a science book the other day. It showed them kind of in between. That's too bad. How do I know that liquids are not in between?
Because it's
I can't hear you.
because like it's not in the middle because it's like a
Why did solids have a definite volume? You told me because the particles are really close. And why can you not compress a solid? You told me the particles are really close. There's no empty space. Can you compress a liquid? Have you ever gone to the store and said, I'm going to buy some compressed milk? It takes up half the space in the refrigerator. I want a gallon of milk compressed to half a gallon. What? I've never heard of that. You're right. You're not going to hear about it. As a matter of fact, when I go home today and I go to a stop sign, I'm really glad that you cannot compress liquids. Because in my brake lines, there's a fluid, brake fluid. And I'm going to try to compress that liquid when I push that brake pedal. I'm going to try to compress the liquid, but it won't. So you know what it'll do? It'll take the force that I put on the brake and send it everywhere in that fluid. Everywhere in that fluid will have that force in there, and it goes where my wheels are, and the brake pads will go, woo, woo. I don't have to go out and put my hands on the wheels. All I have to do is try to compress the liquid, which you can't. And by the way, what do you call it when you use a liquid and you try to compress it? And you can't, but it causes force to be multiplied many, many times. It's how backhoes work. It's how an airplane steers it. It's how a car does the brake. What do you call it? Starts with H. All right, ever heard of hydraulics? That's what that is. Hydraulics. All right, so, what time is it? Are we done already? Oh, I'm sorry. Hey, tonight, great night to work on your drawings, okay? Tomorrow, I'm going to get you I might review this a tiny bit, and then you have the rest of the period to study, do homework. I really would get in groups and study for the test. All right, thank you very much.